Morning, everybody. First off, thank you to the conveners for giving me the opportunity to present via presentation rather than poster. It'll make a lot of the videos a lot more enjoyable. And then secondly, I would like to just thank the big list of co-authors. I'm going to talk today about a lot of geotechnical work that we've been doing in Norway at the Norwegian Geotechnical Institute. And it's taken a lot of people to build up our knowledge in this lunar area over the last 2 years. So in particular, Alex Gervais has worked on a lot of the simulations that you're going to see today. He's now at the Inspire Institute in Ecuador, and Santiago Quinteros has been running a lot of our lab work. So what you're looking at here is a simulation of a cylinder filled with what we call digital grains, but these are real grains that come from CT scans of Apollo 14 sample 14163. And this is a very common experiment that we do in geotechnics called the angle of repose. So you tip the cylinder over 45 degrees, you let it sit there for 4 seconds, you tip it back up, and then you look at the angle that the material leaves. And so this angle is dependent on the size and the shapes of the grains. It's not necessarily equivalent to what we call the internal friction angle, which tells us about the maximum shear strength that granular materials can sustain. And it has a wide range of applications. So for example, the previous speaker just talked about flowability. But this sort of tells you about, in the loosest state of the soil, angles greater than this, the material will flow rather than be in a solid state. And so I'll just give you the highlight of the talk right now, but we've been studying how these materials behave using lab measurements to calibrate numerical simulations, which are digital twins. And this is just an example showing what happens to this particular experiment if we vary the gravity. And this is interesting because you see that this angle increases. And on Earth, there's this very simple relationship that people have used for a long time, where you take the roundness of the grains, the average roundness, and that'll tell you the angle of repose. There's no gravity in that relationship. And so if we're going to take things like this that we've learned over years of doing geotechnical work on the moon, or on Earth, sorry, and apply it to the moon, we need to think about some other things that maybe haven't been thought of in the past. And we know that we see this kind of high angle of repose because of stuff that we learned in the 70s with Apollo and Luna. So this is just an example of a small excavation with a very steep pit telling us that this soil has high cohesion. Okay, so quickly about NGI, since lots of people maybe have never heard of us. We're new to getting into the space stuff, but we're a geotechnical group. We're headquartered in Oslo, but we also have offices in Perth and Houston and all around the world. I work in the natural hazards group, but we have quite a few people throughout the Institute that are just interested in lunar stuff. So there's about 20 of us that have been doing things over the last couple of years. Our main goal is to make solutions for industry and society so that we live and build on safe ground. And this cartoon in the upper right is all the different types of infrastructure things that we do on Earth. And we've slowly been thinking about what we could do on the moon. And so here's a new graph we made. And with that, I would just like to thank the two groups that have been sponsoring this research, the Norwegian Research Council and the Space Agency in Norway for the last 2 years. So moving on, we've seen lots of talks now about Mara and Highland simulants. Normally when we talk about simulants and thinking about what we want to do on Earth in terms of geotechnical properties and using those as analogs, we categorize things into these two things. But I think over the last couple of days, we've all seen the regolith is much more heterogeneous. And I'm not convinced that just using those two is a good way to define or describe all the geotechnical properties that we might encounter up there. All of the information that we currently have geotechnically comes from these landing sites, either experiments that were done there or return samples. And this is just a nice, not true color image, but I like to look at it and say, just by eye, have we sampled all the different colors? No way. So there's a lot to be learned still by collecting samples in all these other areas. So what we do know, I just said, we've done geotechnical experiments, seismic experiments, et cetera, on the moon. We've also brought back lots of samples and studied those in the lab. And I think it's important to keep in mind that upcoming missions are going to provide new in situ data and potentially return samples. So I do think as a community, we should argue for return samples that we can continue to analyze, because a lot of the geotechnical work done in the 70s, the methods have changed dramatically since then on terrestrial applications. We have new types of standards and we do a much better job. So with that in mind, NGI's focus right now is to just improve geotechnical characterization of simulants and try to get ourselves ready so that we could be partners in analyzing future return samples. And we're doing that through the lab and through simulation. And so I'll just quickly talk about the lab and then we'll go on to the simulation stuff. But the interesting thing from a geotechnical point of view is considering the in situ stresses that we're going to encounter on the lunar surface when we go up there and do things. Anything we want to do, move it around, beneficiate it with whatever. The interesting thing is because of the low gravity, we have very low effective stresses. So within the top few meters, we only get up to effective stresses of a few kPa. That's quite different than on Earth. And so what we've had to do, this is just a list of what we've currently achieved, but we do advanced testing. These are different types of strength tests that we do on granular materials. And we can get down to 1 kPa for an odometer, but then let's say down only to 10 kPa for a triaxial cell. And part of that is just, we can't, the end caps of a triaxial cell are too big right now. And so if we want to go to lower effective stresses, we have to kind of actually just redesign all of our hardware and rebuild things. So aside from the lab, I'm going to talk today about simulations. And the reason for that is because of the lunar environment. So internally, we call this the selenotechnical environment or selenotechnics because it's quite different than Earth. So this idea that it's just a one-to-one geotechnics is going to work on the moon, I'm not convinced that's true. Here's just a list: low pressure, low humidity, low gravity, and extreme temperatures. Materials behave much differently in this environment. And in addition to that, we have a very different, let's say, weathering or modification processes that we don't get on Earth. And so back to this idea of two simulants, we talk about high fidelity simulants of Mare and Highlands, and then really expensive simulants where you actually try to incorporate agglutinites and some of these other interesting things that come from these weathering processes. So for us, the question is, how can we account for this, or how do we account for this? And so in a very quick way, I'll just say what we're doing are building these digital twins of lunar soils. To build this digital twin, we use a method called the 3D level set discrete element method, 3D LSDM for short. What this allows us to do is micromechanics at the grain scale, and we can do multi-physics micromechanics. So this is just some highlights, but on the left, you're seeing two negatively charged particles and a positively charged particles following electrostatic forces. We can incorporate this now into our physics. This one in the center is grain breakage. So the walls are moving in on this and you're going to break the grains. This is very important actually because of the very interesting shapes that you see on the lunar regolith. And on the right was a video showing thermal expansion and heat transfer. And this is now a combination of 3D LSDM plus finite element modeling that we haven't published anything on, but Alex has been working on this for the last couple of months. So digital twins, the idea is that we can do something in the lab, we can calibrate one of these simulation models, and then we can go and we can change the boundary conditions, we can change the effective stresses, we can change the strain rates so that these materials go from, let's say, solid to non-Newtonian. And this is just an example of sand, an example of 2300 LHS1 silt grains on the right, at slower strain rates in a compression test. And it's just to show you what we're talking about. This is a nano CT scan image here. So there's a bunch of these silt grains, so smaller than 60 microns, in a nano CT scan at the University of Oslo. And this is just an example of some slices of the micro CT that we have in our facility, and then the nano CT at the dental school at the University of Oslo that we've been collaborating with. So I'm going to come to this last thing really quick. But because we can analyze all the shapes with these digital grains, it allows us to do some very interesting characterization. So on the bottom, you see histograms of LHS1 compared to Apollo 11 and Apollo 14 samples that we got from our collaborators in NIST. And it's showing you, let's say, size properties, diameter, volume to surface ratio, and volume. We match those very well with the simulants. on top, you see grain shapes. You see roundness, aspect ratio, and sphericity. Those we actually don't match so well. And this comes down to, again, this grain formation process, this modification. And these images on the right are just some of the examples. You get really interesting grain shapes that you wouldn't find on Earth, where we have aeolian erosion processes, things get smoothed down over time. And so all of these need to be taken into account when we're doing the geotechnical strength properties, because they change the internal friction. And these are just some videos of some of the Apollo samples. And I'll just end with this last slide. If you take all of these, let's say terrestrial and simulants, and you plot them in their minimum void ratio, so their densest state, their maximum void ratio, their loosest state, and you compare those to all the Apollo samples, you see that they actually don't line up. And so this is a paper that we have in review right now, but trying to look at what are the differences. And there's now starting to understand and maybe be able to incorporate in simulations. That's it. Thanks.